We're digging into an assessment for a natural gas gathering line.
Yeah, and we've got the triage summary and a briefing doc based on that.
Good sources.
So for everyone listening, the goal here is to really get a handle on why corrosion is a risk in this particular pipeline and what steps are being suggested to manage it.
Exactly. And what's interesting, like you said, is that initially things didn't look too bad.
The baseline assessment seemed okay.
Yeah, under normal steady-state flow, the risk of internal corrosion seemed pretty low. The fluid velocity, the pressure, everything looked like it would prevent water just sitting there.
Okay, so let's start there. The documents, they actually say, the triage assessment confirms a low baseline likelihood of pre-existing internal corrosion damage under conditions of steady-state transport.
So it sounds good.
It does, on paper. But obviously there's a but. What changes things?
The operation. It's not steady state. It uses what's called an intermittent plunger lift.
Okay, what does that mean in practice?
It means the flow isn't continuous. It's more maybe 1 hour of flow every 24 hours, something like that.
Oh, okay. Stop, start.
Exactly. And that is the game changer. Because, as the document puts it, this mode cyclically reintroduces fresh produced water into regions susceptible to stagnant water accumulation.
So every time it stops and starts, it pushes more water into places where it can just sit.
Precisely. And there's a specific spot mentioned.
Yeah.
Probably across the mid-range water body crossing where pipeline inclination supports fluid retention.
So there's a dip in the pipeline, maybe where it goes under a stream or something.
Sounds like it, a low point.
And with that start-start flow, water just keeps collecting there.
Yeah, that low point becomes this sort of persistent wet zone, a hot spot.
So the risk isn't uniform along the pipe. It's concentrated right there because of the operation and the geometry.
Correct.
Okay, so we have stagnant water being constantly refreshed. How exactly does that increase the corrosion risk? What are the mechanisms?
The assessment points to a few key things. First, in those stagnant areas, you can get localized pH suppression.
Meaning the water gets more acidic?
Yeah, essentially.
Yeah.
More corrosive. Then there's the risk of activating pre-existing but dormant corrosion damage.
So like poking a sleeping bear, minor flaws get aggravated.
Yeah, repeated wetting and potential chemistry changes could kickstart things. And third, these conditions are just ideal for under-deposit corrosion.
Where stuff settles out and corrosion happens underneath.
Exactly. Sediment, potentially other gunk, water sits there, things settle, and corrosion starts under that deposit layer. It can be quite nasty.
So multiple corrosion mechanisms all linked back to that cyclical water introduction in that specific low spot. Now, is this just a theoretical worry based on the operating mode, or is there real-world evidence supporting this concern?
That's where the regional context becomes really important. The briefing note mentions it.
What does it say?
It says, regional performance confirms internal corrosion failures in pipelines of similar vintage. So pipes built around the same time, early 2000s.
Okay.
After approximately 20 years of service. And crucially, these failures were attributed primarily to inadequate mitigation of produced fluids rather than external factors.
So history in the area shows that this is a real risk, and standard approaches haven't always been enough for this kind of situation.
Pretty much. It really underlines why a specific targeted approach is needed here. What worked elsewhere, or what seemed okay on paper, wasn't cutting it for these types of operations.
And it sounds like whatever they were doing before wasn't tackling this specific stagnant water problem effectively.
Data affirms that historical mitigation strategies have not effectively addressed stagnant water corrosion risks, which leads right into reinforcing the importance of adopting the MEG slugging program.
Okay, so that brings us to the solution. What is this recommended plan? Sounds like two parts.
Yeah, a two-pronged strategy. First is MEG slugging.
MEG.
Monoethylene glycol. It's basically an inhibitor, stops or slows down corrosion.
Okay. How often, how much?
The recommendation is a 30-liter slug every 30 days, so monthly.
A regular dose. And there was something about timing this with pigging.
Yes, that's critical. The note says, if field operations include pigging, MEG slugging should be performed immediately following the pig run.
Why? What's the benefit of doing it right after?
That's the second part of the strategy, is where they run a tool, a pig, through the line.
To clean it out?
Yeah, exactly. To physically push out liquids, solids, water films that might be sitting there. So you run the pig, clear the decks, so to speak, and then immediately follow with the MEG slug. This helps maximize displacement of water films and promote a non-corrosive MEG water mixture in stagnant zones.
I see. So the pig clears the path, gets rid of the stagnant water and gunk, and then the MEG comes right behind it to treat the now exposed pipe surface, especially in those tricky low spots.
Precisely. It ensures the inhibitor gets where it needs to go and can mix effectively with any remaining water to make it less corrosive.
And the pigging itself, is that also recommended monthly?
Yes, the recommendation is monthly pigging if feasible because it supports effective removal of solids and stagnant water films.
So the combination is key. The physical cleaning and the chemical protection timed together.
It's a synergistic approach, tailored specifically to combat that stagnant water issue caused by the intermittent operation.
It's interesting, too, what they didn't find. The assessment specifically ruled out some other potential causes, right?
It notes no evidence of accelerated corrosion linked to upstream debris contaminant ingress attributable to detrimental well startups.
So it wasn't about junk coming from the well during startup or anything like that. The focus stays squarely on managing the internal environment created by the regular cyclical operation.
Exactly. It helps narrow down the problem and confirms the mitigation strategy is targeting the right thing, the internal hydraulics and water handling.
Okay, so let's try and sum this up for our listeners. We started with a pipeline that, under normal continuous flow, seemed low risk for internal corrosion. But the actual way it operates, this intermittent stop-start plunger lift cycle, completely changes the picture.
It does. It creates a situation where water is repeatedly introduced and allowed to become stagnant in a specific low-lying section.
And that stagnant water leads to localized acidity, potentially activating old damage and creating spots for under-deposit corrosion. A real hotspot.
Yep. And regional experience with similar pipelines confirms this isn't just theoretical. It's a known failure mode if not managed properly.
Which leads to the proposed solution, a monthly routine. First, run a pig to clean out the line, remove stagnant water and solids.
And then immediately follow up with a slug of MEG inhibitor to protect the pipe surface, especially in those vulnerable low spots.
It's a proactive plan, seems field executable, and directly addresses the risks identified in the assessment and backed by regional data.
Exactly. It really shows how crucial it is to look beyond just the design specs and understand the real-world operational impacts on integrity. You need that tailored approach.
Absolutely.
It really speaks to the need for continuous vigilance and a really deep understanding of how we operate complex systems. Things aren't always as straightforward as they seem.
Definitely something to think about.